Hello friends and welcome to this video. With this video we are going to start a new chapter in the subject Advanced Digital Signal Processing. The chapter here it is titled Adaptive Filters. This is the sixth chapter. We are already covered with 5 chapters listed as Digital Spectrum, Multi-Rate Digital Signal Processing, Discrete Time Random Processes, Power Spectrum Estimation, and just now we are covered with the 5th chapter that it was titled Linear Prediction and Optimum Linear Filters. So here we are having the first topic that I am going to address for adaptive type of the filtering is adaptive filtering system identification. It is basically the introduction to the adaptive type of the filtering here. So as we see here we have 4 terms to this topic title. First one is the term adaptive, second one is the filtering, third one is the system, fourth one is the identification here. So now system identification definitely we shall do if we club these two particular terms. First of all, it is very necessary to understand the first two terms here, adaptive filtering. So out of the 4 we have to group them into the 2, adaptive filtering and then system identification here. So with respect to the second term, that it is the filtering from the first group, I hope you are very well familiar. Right from the subject into the most possibly 6th semester or the 5th semester, signals and systems, we have been continuously dealing with the filtering operations for betterment of the signal interpretation, extraction of the information, and lot of applications we have there. Now the first term to this particular group is new, that it is adaptive here. So I just tell you, adaptive means non-stationarity here. If you talk about stationarity, if certain quantity is a constant quantity with the changes into the time or different situations, if it is not getting changed, so we say that the thing is stable, it has a stationarity here. But if there are changes with respect to the time and with respect to the other parameters of the system as well here, so it means the concerned thing with your hand is of the type adaptive here, and here we are having a consideration of adaptive type of the filtering. So the basics of the filtering what we have learned till date will be the same here, but it will have a different nature that will be of the adaptive type. So it is going to deal with the non-stationarity of the signal fed as input to the system developed for processing that particular type of the signal here. So further we shall be focusing on the system identification of the type of adaptive of course here. So while having introduction to this particular domain, I will just give you a brief difference between what we have learned so far in the previous 5 chapters and from this topic onwards what changes we have here. So up till now in the previous 5 chapters we have dealt with the variety of the different problems here. For example, the problems can be listed as of signal modeling, the Wiener filtering, spectrum estimation. So spectrum estimation we have covered into the 4th chapter. It was power spectrum estimation. Variety of techniques thereupon we have dealt with. The Wiener filtering just now we have covered in the previous chapter, that it was linear prediction and optimum linear filters. Signal modeling is also the generalized one. So if we talk into the more details, for example for the case of signal modeling, if we talk, we can have one assumption thereupon that the signal to be modeled could be approximated as the output of a linear shift invariant filter that can be denoted by h of n here, with an input that is either of unit sample type. If it is the case of the deterministic signal, we know the difference between deterministic and the random signal, or if it is of the type stationary white noise for the case of stochastic signal modeling here. So the very important point to be noted here is that for dealing with these different types of the problems covered into the previous chapters, the assumption was that the signals being analyzed are all of the stationary type here. They are not supposed to change their details with respect to the changes into the time as well as the other parameters. but the case is different in this particular chapter. Here we are going to focus on the non-stationarity. That is why the type adaptive here. So here we are talking about the shift varying type of the filters, that we can call it to be the adaptive type of the filters here. So discussing with respect to what we have covered previously, I can say that since the signals that arise in almost every application practically will be having certain extent of non-stationarity, so whatever approaches and techniques we have been learned in the previous 5 chapters, it was considering with the stationary type of the data will not be the appropriate option here. So a brief modification we can do thereupon, that is to have consideration of certain intervals for which we can assume that the process is approximately stationary here. But this simple modification will also be having a lot of limitations for several of the reasons. So today's topic is not to focus on all those particular reasons, but to directly enter the understanding of the adaptive filtering system identification here. So here we begin with the non-stationary assumption as the outset here, and the further analysis will be based on this particular theme only here. So let us discuss about one point from the previous chapter, that it was for the Wiener filter design here. So considering the Wiener filter designing that just now we are covered in the previous chapter, linear prediction and optimum linear filters here, the context can be within the scope of non-stationary process here. So let us denote W of n for representation of the unit sample response of the finite impulse response type Wiener filter. In the previous chapter we have covered both FIR for finite impulse response and IIR for infinite impulse response here. So this is supposed to produce the minimum mean square estimate for a desired process that can be denoted by D of n here. So this is one of the very important metric, minimum mean square estimate for the desired process here. So this estimate can be mathematically denoted with the help of cap over the head of the representation of D of n here. So I express it as D cap of n to be the summation having the index variable k ranging from 0 to small p for the multiplication of W of k with x of n minus k here. So if x of n and the D of n original are jointly wide sense stationary processes with the error or the difference denoted as E of n, that is equal to D of n minus D cap of n, the filter coefficients that minimize the mean square denoted by capital E of mod square of E of n are found by solving the Wiener-Hopf equations already introduced in the previous chapter here. So these Wiener-Hopf equations can be represented in the form capital R suffix x in multiplication to W, that is equal to small r suffix dx here. So if the desired signal D of n and x of n are here considered to be of the type non-stationary, here it is our focus. So that time the filter coefficient that minimize this minimum mean square error denoted by capital E of mod square of small e of n will depend on small n, the representation of the discrete time domain here, and the filter will be of the shift varying type here. So here we denote the expression D cap of n is equal to the summation k is equal to 0 to p or the multiplication of W suffix n of k into x of n minus k. So the difference into the previous expression and this expression is that W of k, that it was originally, now here it is represented by W suffix n of k here. So W suffix n of k, here it is the value of the kth filter coefficient at the time n here. Now we can make the use of a vector notation. So the estimate we express into the new form, this will be d cap of n is equal to w suffix n to the power we represent capital T in multiplication to x of n, small x of n. So here w suffix n can be a transpose of the set of the coefficients listed as w suffix n of 0, w suffix n of 1, w suffix n of 2 and so on up to w suffix n of p here. And here we have the representation of x of n, also a transpose of the coefficients denoted x of n minus 1, x of n minus 2 up to x of n minus p here. So here if we compare the design of the filter which is of the adaptive type and the design of the filter that we were dealing in the previous chapters, so we can say that the design of the shift varying filter, adaptive filter, is much more difficult than the design of the shift invariant filter for the Wiener filter, the example we are dealing with, where for each value of n it is necessary to find the set of optimum filter coefficients denoted by w of k in the suffix w is having small n, for k is equal to 0, 1, 2 and so on up to p here. So here the problem may be simplified by considerably level if we relax the requirement that w suffix n minimize the mean square error at each time n and consider instead the coefficient update equation given by the new form. Here we have the new form w suffix n plus 1 is equal to w suffix n added by delta w suffix n here. So in this representation, delta w suffix n, which is the second term on the right hand side here, this is just a correction that is applied to the filter coefficient w suffix n, the first term on the RHS at the time n, to form a new set of coefficients denoted by w suffix n plus 1 here. This will be at the time n plus 1. Now here we can visualize a block schematic. This block schematic is of the adaptive filter consisting of the shift varying filter denoted by w suffix n of z and an adaptive algorithm for updating the filter coefficients denoted by w suffix n of k here. So in this block schematic you see the discrete time random process in general, the input to the system is denoted by x of n here. As we discussed the shift varying filter, here it is the block with the function representation of capital W suffix n as a function of z here. Here it is the use of the adaptive algorithm as just now I have talked about. And see here the role of d of n, the original signal, and the estimate d cap of n. The difference is calculated to be e of n, which is fed as input to the second block adaptive algorithm, which is making the computation of the filter coefficients denoted by w suffix n. And as with the help of the previous expression, the delta w suffix n is fed as input to the first block of capital W suffix n of z here. Now as just now we have talked about the Wiener-Hopf equations. So the most important point here will be solving the Wiener-Hopf equation will need that the two estimate metrics here, those are the autocorrelation metric and the cross correlation metric. So generally the autocorrelation metric can be denoted by small r suffix x of k, the cross correlation metric by small r suffix dx of k here. These should be known values here, and since these two ensemble averages are typically unknown in the practical cases here, so it becomes necessary to have estimation of these two metrics from the measurements of the processes here. So here we can have the use of the estimates into the form of the two expressions. First one is for the autocorrelation and the second one is the cross correlation here. As these are the estimates, these have been shown with the caps over the head of the representation of the autocorrelation. So autocorrelation can be denoted by r suffix x of k, whereas its corresponding estimate can be denoted by, as this is the estimate here I have mentioned, r cap suffix x of k here. Similarly, r suffix dx of k is the representation of cross correlation. R cap suffix dx of k is the estimate of the cross correlation here. So for the estimate of autocorrelation, it is computed by 1 upon capital N summation of n is equal to 0 to capital N minus 1 for the multiplication of the original input x of n into the complex conjugate of x of n minus k. Whereas for the cross correlation estimate, it is equal to 1 upon capital N summation n is equal to 0 to capital N minus 1 for multiplication of the desired signal d of n into the complex conjugate of x of n minus k here. So as practically we are having a consideration that whatever the environment we have considered here is supposed to have changes with respect to the changes into the time here, there it is a need to always update these two estimates continuously. So here we have the set of rules which we can term to be the algorithm here. So this will be the algorithm that will be used for the adaptive filter, and the steps in this particular algorithm one by one I will tell you. So the first, second and third step we have to go for here. So the adaptive filter should have the following properties or the steps here. The first one is that in the stationary environment, the adaptive filter should produce a sequence of correlations delta w suffix n in such a way that w suffix n converges to the solution to the Wiener-Hopf equations that mathematically can be expressed as limit small n extends to the infinity or w suffix n that will be equal to the inverse of capital R suffix x into small r into dx here. The second point is that it should not be necessary to have knowledge of the signal statistics, that is autocorrelation Rx of k and the cross correlation R suffix dx of k in order to have computation of the difference by delta w suffix n, and the estimate of this particular statistics should be built into the adaptive filter here. And the third point is that for the non-stationary signals, the filter should be able to adapt to the changing statistics and track the solution as it evolves into the time. Now, as just now we are covered one block schematic to represent the adaptive filter consisting of a shift varying filter and the adaptive algorithm, the steps where we have described in the points 1, 2 and 3 here. So this underlies very important issue while implementation of such an adaptive filter, that there it is a requirement that the error signal that can be denoted E of n, in the previous representations also we had the same. So this should be available to the adaptive type of the algorithm, and since this E of n allows the filter to measure the performance and determine how the filter coefficients should be modified, without E of n the filter would not be able to have adaptation here. So in some of the applications, acquiring the desired signal d of n is a straightforward thing here, and that makes the evaluation of E of n very easy here. So for that purpose, let us have the consideration of one example where the problem of system identification we visualize with the help of this particular block schema. So here, as you can see, the first block to which x of n is fed as input is called as the plant here, and the plant produces an output denoted by a d of n, which is in response to the known type of the input that we have represented by x of n. The only motive here is for the development of a such model for the plant we can denote it by capital W suffix n of z that produces a response d cap of n that is as close or very similar as possible to the model for the plant we have denoted by d of n. Now in this block schematic there it is one new representation that you see v of n here. So this is in order to have account of the observation noise in the measurement of the plant output. So this is the additive noise source denoted by V of n. So here we are going to have consideration of the problem of the interference cancellation where the signal d of n is observed in the presence of the interference signal V of n here. So x of n will be d of n added by V of n. Now as we know that d of n is unknown to us. So therefore the error sequence cannot be generated directly. Therefore for the estimation of d of n, let us have another block schematic that will have generation of the sequence that may be used by the adaptive filter. So these are the different points already we are covered, and here it is the block schematic. So let us make the consideration that d of n and v of n are the real valued uncorrelated zero mean processes, and additionally suppose that the d of n is narrow band process and that v of n is a broadband process with the autocorrelation sequence that can be approximately 0 for the lags k greater than or equal to k suffix 0. So here the mean square error that can be formed by taking the difference between the original x of n and the output of the adaptive filter that can be denoted by y of n will be expressed by the mathematical expression here it gives on the left hand side capital E of square of small e of n that is equal to capital E of square of the bracket that has d of n added by v of n minus here we express y of n. To the next step we express it to the form, the first term it will be capital E of v square of n added by the second term that will be capital E of square of d of n minus y of n, and at the last we have twice of capital E of estimate of v of n multiplied to the bracket that has difference d of n minus y of n. So as we have the assumption that v of n and d of n are totally uncorrelated to one another, that is why we express capital E of v of n into d of n is equal to 0, and therefore the last term that we see on the right hand side will be having the new form. So instead of twice of capital E or multiplication of v of n to the difference d of n minus y of n, we can denote it as minus twice of estimate of v of n into y of n here. Additionally, since the input to the adaptive filter is here denoted by x of n minus k suffix 0, so that time the output y of n can be expressed as y of n is equal to the summation k is equal to 0 to p for w suffix n of k multiplied by x of n minus k 0 minus k, which can further be also expressed to the form summation kept as it is for k is equal to 0 to p, w suffix n of k also kept as it is. Instead of x of n minus k0 minus k, we substitute with the help of a square bracket that has the first term d of n minus k0 minus k added by v of n minus k0 minus k. So therefore the estimate of the product v of n into y of n will be equal to the summation k is equal to 0 to p for w suffix n of k multiplied to the square bracket that has first of all estimate of v of n into d of n minus k0 minus k added to estimate of v of n into v of n minus k0 minus k. So at last, as we have the consideration that v of n and d of n are uncorrelated to one another, also the uncorrelation of v of n with V of n minus k0 minus k is considered, so that time the estimate of V of n multiplied to Y of n will be equal to 0, and now the mean square error can be represented by simply estimate of E square of n, that is equal to estimate of V square of n added by capital E of square of the bracket that has the difference d of n minus y of. So from this expression it can be concluded that minimizing capital E of E square of n is very equivalent to minimization of capital E of square of the difference d of n minus y of n. The mean square error between d of n and the output of the adaptive filter denoted by y of n. So therefore the output of the adaptive filter is the minimum mean square estimate of d of n. So this was all about the first topic from the sixth chapter. The topic it was adaptive filtering system identification, which I hope is clear to you people, that I have explained with the help of the block schematic for the system identification here. By the next lecture we shall continue in the same chapter adaptive filters, and the topic it will be FIR adaptive filters. Thank you.